So in section 5 we're going to look at RSA and regioselective reactions of alpha-beta unsaturated carbonyl compounds, and we'll start by looking at the formation and reactivity of alpha-beta unsaturated carbonyl compounds in section 5.1. And alpha-beta unsaturated carbonyl compounds are readily available starting materials prepared in high yield via aldol-type condensation reactions of aldehydes, ketones and or esters. So here we have two readily available starting materials. Here we have an alpha-beta unsaturated ketone, alpha-beta unsaturated ester, which are commercially available. In general terms, if we want to make alpha-beta unsaturated carbonyls, one easy, straightforward method is via an aldol condensation reaction, where we disconnect through the carbon-carbon double bond, and we go back, in this case, to an aldehyde and to this methyl ketone in the presence of base, and then in the second step, acid and heat, where we get a condensation reaction taking place to lose water. We can form the alpha-beta unsaturated carbonyl. So these compounds are either commercially available or very easily prepared. And conjugation of the CO double bond with the CC bond means that alpha-beta unsaturated carbonyls are susceptible to attack by nucleophiles at both the 2 and the 4 positions. So in this diagram you can see the numbering starting with oxygen as 1, 2, 3, 4. Attack at the 2 position is a classic nucleophilic addition of the carbonyl, and we describe that as 1,2 addition. More surprising though is attack at the 4 position, so-called 1,4 addition. And we can explain this through resonance. If we look at resonance forms of the alpha-beta unsaturated carbonyl, push the electrons onto oxygen, and you'll see in this resonance form we have a positive charge on the carbon at the 2 position, and in this resonance form we have a positive charge on the carbon at the 4 position. An attack at the 2 position, called 1,2 addition, well, attack at the 4 position is called 1,4 addition, conjugate addition, or if we're using carbon nucleophiles, it's called the Michael addition. An addition of carbon nucleophiles such as enolate ions or organometallics leads to CC bond formation, and so they're very important in synthesis. And there are a number of factors that will affect and influence whether a nucleophile attacks 1,2 or 1,4. In other words, the regioselectivity of the addition, and this includes steric effects, namely the size of the nucleophile, and also the type of nucleophile, for example the type of organometallic reagent that you're using. So we'll start by looking at 1,2 addition, so it's direct addition at the CO double bond, and Grignard reagents mainly undergo reaction at the CO double bond of an alpha-beta unsaturated carbonyl. In this example you'll notice here that this Grignard prefers to attack at the 2 position, and then on protonation we form this tertiary alcohol in 79% yield with just 21% attack at the 4 position. And this addition is described as being under kinetic control because the stronger CO double bond is broken, whereas the weaker carbon-carbon double bond is retained. So let's now compare that with 1,4 addition, or conjugate addition, or Michael addition, and here we're going to use organocopper reagents, or cuprates, and these mainly attack at the CC double bond in this 1,4 addition process. And if we look at what's described as a simplified mechanism, here we have a cuprate reagent. We can take the electron density from one of these copper-carbon bonds. We can attack at the 4 position, pushing the electron density onto the oxygen, so we form an enolate ion, and that enolate ion on protonation gives us this ketone. You'll notice this is highly regioselective, 98% attack at the 4 position and just 2% attack at the 2 position. This addition is described as being under thermodynamic control because the stronger CO double bond is retained, whereas the weaker carbon-carbon double bond is broken, i.e. in this case the more stable product is formed. So let's now have a look at how you'd make an organocopper and a cuprate, and classically you can make them from organolithium compounds. So if we take copper 1 iodide with this organolithium, we can then make, in this case, methyl copper, and then if we add that to methyl lithium, we could make lithium dimethyl cuprate. And the methyl copper reagent is usually, in this case, less reactive than lithium dimethyl cuprate. Let's now look at an example of this in synthesis, and here's my target molecule, 3-propyl cyclohexanone. I'm going to disconnect now the side chain from the ring, put a plus on the ring and a minus on the side chain. Synthetic equivalent for this will be the alpha-beta unsaturated ketone. The synthetic equivalent for this will be an organometallic, and because we want to attack at the conjugate or 1,4 position, we're going to now use a cuprate reagent. Let's now look at one other example of this type, where we're now looking at sequential Michael addition and alpha methylation. And this is a very powerful method in synthesis because it allows the formation of 2 carbon-carbon bonds. In this particular starting material, where we have an acetyl protecting group, we're going to first disconnect the carbon-carbon bond. We're going to put a minus on the carbon atom next to the carbonyl and a plus on the methyl group. If we now disconnect off the other side chain, we can now introduce a double bond into the ring and put a minus onto the alkene side chain. If we now look at the forward synthesis of this reaction, to get 1,4 addition, we need to use a cuprate or a copper reagent, organocopper reagent. Here we're going to use lithium divinyl copper to introduce the vinyl group at the 4 position. We form this intermediate enolate ion, which in a subsequent reaction with iodomethane introduces the methyl group at the 2 position. If we look at the stereo selectivity, you'll notice that the vinyl group goes into the top face to avoid the bulky acetal, which is protecting the bottom face. And then the second step, this SN2 reaction, you'll notice that the methyl group reacts to go on the bottom face of the molecule to avoid the bulky adjacent vinyl group. This is a really nice example where we're combining both Michael addition and alpha methylation, and we're making these chiral centers stereo selectively. So the preference for 1,2 versus 1,4 addition can be explained by considering the orbitals that are involved in the principle of hard, soft nucleophiles and electrophiles. And the carbon atom directly attached to oxygen has a high delta plus density and is described as being a hard electrophile, and it preferably reacts with a hard nucleophile which has a high delta minus density. And the R group in a Grignard has a high delta minus density because it's adjacent to a highly electropositive magnesium atom, and so a Grignard is a hard nucleophile. In comparison, the carbon atom at the 4 position has a low delta plus density. It's described as being a soft electrophile, and it preferably reacts with a soft nucleophile which has a low delta minus density. And the R groups in a cuprate have a relatively low delta minus density because they are adjacent to a weakly electropositive copper atom, and so a cuprate is a soft nucleophile. So have a look at another example in synthesis, namely to make dimethyl 2,3-oxocyclohexyl malonate. Again, we're going to disconnect the side chain from the ring, put a plus on the ring and a minus on the side chain. The synthetic equivalent for this will be the alpha-beta unsaturated ketone. The synthetic equivalent for this, well, this is like an ester enolate ion, can be derived from the parent diester, or in this case it's called a malonate, and we deprotonate in the middle of the 2 carbonyl groups. This is described as being a soft nucleophile because the negative charge can be spread over both of the carbonyl groups. It's delocalized. So this is a soft nucleophile. As a consequence of that, it will react at the soft electrophilic position of the alpha-beta unsaturated ketone, which is the 4 position. So in the forward reaction, the anion will attack at the 4 position, pushing the electron density onto the oxygen. We form an intermediate enolate ion, which on protonation then forms the target molecule.